test of a planetary defense technique called kinetic impactor, and it's going to smash itself into the moonlit Dimorphos, which orbits the asteroid Didymos, in order to change Dimorphos's orbit and show that we can deflect incoming asteroids if we need to. I lead the group of astronomers that are going to measure how much DART changed Dimorphos's orbit using ground-based telescopes all over the world. This is an animation. You can see Didymos and Dimorphos as one point of light. These curves show the brightness change due to Dimorphos moving in front of and behind Didymos. We can tell how quickly Dimorphos is moving around Didymos. We make these measurements before DART arrives, and then this is the same technique that we'll use after the impact to determine how much we've changed the orbit by. I make music. A lot of it, as you might imagine, has nothing to do with science, but a lot of it does. You know, I'm not immune to the charms of writing a gimmicky science song every once in a while. So I did write a song about DART.
The mission goes by the name of DART. That's our asteroid redirection test. And just one flick should do the trick.
A lot of scientists definitely have a creative side. A lot of us write, a lot of us are in bands, or there's a lot who paint, and I think having that creative part of your brain definitely helps in science, just as much as it does in art.
Practice planetary defense with DART.
Hi everyone, I'm Josh Handel and I'm a Public Affairs Officer here at NASA. And I'm so excited to be joined today by Andy Rivkin, who you just had the opportunity to meet. Andy, thank you so much for joining us today.
It's a pleasure, Josh. Thanks for having me.
Of course. Andy's here to answer your questions about planetary defense at NASA and the DART mission. If you have a question you'd like to ask Andy about planetary defense or DART, send it in using the hashtag AskNASA or by writing in the comment box of wherever you're watching today's broadcast. So Andy, we just learned a little bit more about you from your video and your work with DART, but can you please tell us a bit more about why this mission is so important?
Sure, it's my pleasure. Asteroid impacts into Earth are one of the only, maybe the only, natural disaster that we can predict very far ahead of time and that we can also do something about. So there are a few different ways that people have come up with to address asteroid impacts and prevent them from happening. DART is a test of a technique called the kinetic impactor, where we basically take a spacecraft and we ram it into an asteroid. And by doing that, we change the orbit of the asteroid so that, in principle, if something were coming our way, we could move the orbit so that it was no longer coming our way.
Wow, that's a great answer. Thanks, Andy. And I actually see that we're already starting to get some questions in from our viewers. So we're going to go ahead and get started. And as a reminder, if you have a question for Andy, you can send it in using the hashtag AskNASA or by writing in the comment box of wherever you're watching today's broadcast. All right, Andy, are you ready?
I am. Let's go for it.
Our first question comes from Robert Clauderson on Facebook, who asks, will we be able to know what the composition of Dimorphos is by looking at the light from the impact of DART?
That's a great question. We have a pretty good idea of what the composition of Didymos is, the main body. Our theories of how asteroid moons form suggest that Dimorphos should be made of the same material. When the DART impact into Dimorphos occurs, we expect there to be a lot of debris that's thrown out into space by that impact. I don't think we're going to be able to directly measure the composition of that dust, but certainly we're going to try. And then the European Hera mission will be showing up a few years after the DART impact. And they will be able to directly measure the composition of Dimorphos. So they'll be able to confirm a lot of what we've been thinking.
So it sounds like we have an idea of what it's made of, but we won't really know until we get there. Is that correct?
Yeah, that's correct. We think that Didymos is made of the same kind of material as what we call ordinary chondrite meteorites. So they're very common material that falls to Earth. We think it's the same kind of composition that the asteroid Itokawa has, that the asteroid Eros has, and that the asteroid Apophis has. So it's a common material that is pretty commonly what falls to Earth.
Our next question comes from Indy Magoo on YouTube, who asks, Would you try to find an object with a higher albedo so it would be easier to track?
So for those out there that are not familiar with what albedo is how reflective a surface is. So something like snow is very reflective, has a high albedo, as we say. Something like tar or a charcoal briquette has a very low albedo. It's very dark. As suggested, high albedo objects are more visible from far away. One of the things in asteroid science is we don't always get to pick what our targets are like. The targets pick that for themselves. So Didymos has an albedo we think of about 15 to 20%, so typical for rock. And Didymos has so many other great properties for carrying out DART that it's kind of, even regardless of albedo, it was clearly going to be the place to go.
Our next question comes from Viswadeep Natarajan on YouTube, who asks, what are possible options to deflect a massive-sized asteroid?
That's a great question. The answer depends a lot on how much warning time we have before we have to deflect the asteroid, and the size of the object. So DART is part of kind of an overall national strategy for dealing with asteroid impacts. One of the other pieces is doing a search to find objects that are out there that might be hazardous and find them as soon as we can. The longer the warning time we have, the more different options we have. And some of the options might be, if an object is small enough that we just say, okay, it's going to burn up in the atmosphere, we're not going to worry about it. We'll just enjoy the meteor that it makes, and maybe pick up some little pieces if they make it to the ground.
So DART is obviously testing one form of asteroid deflection technology, but it sounds like a key point for it to work is that we would need to find a potential threat early. Is that correct?
Yes, that's kind of true for almost any of the techniques that people have considered. There are other techniques, including civil defense, which would in fact be go and wait it out in the basement. The most powerful tool we have in our toolbox is to use a nuclear device to detonate nearby a threatening asteroid, vaporize part of it, and deflect it that way. But we obviously want to have as many different tools in our toolbox as we can, because we're going to be faced with different scenarios, and so we want to make sure we have the right tool for the right job.
So kind of following up on how we're going to know DART will work, Videographer on YouTube asks, will we measure before and after impact, or will we only look at accelerations at the moment of impact? And how will we know these measurements how will these measurements be taken?
It's another great question. A lot of great questioners out there. From the Earth, Didymos and Dimorphos are going to appear as a single point of light. We're not going to see them separate. So what we can do, and what we will do, is measure the brightness of the system as Dimorphos goes around. And from the point of view of the Earth, Dimorphos will move in front of and behind Didymos, and that will make the brightness go up and down as it does that. We've been measuring that brightness for years. People have been measuring it in some form or another probably since 2003, but we've been measuring it for this project since 2015, so we know the period of that orbit very well. After the impact, we're going to keep measuring it. We're going to keep measuring the brightness of this point of light going up and down. We're going to measure the new frequency with which the brightness changes, compare that to the pre-impact measurements, and be able to say, okay, the orbit period was 11 hours and 55 minutes before the impact. Now it's 11 hours and 45 minutes or 38 minutes or whatever it is. That gives us the information we need to know how much we changed the orbit.
Our next question comes from Alan Ranke on Facebook, who asks, what are the characteristics of the spacecraft itself?
The spacecraft is about the size of a vending machine, not counting the solar panels. So it's 2 meters by 2 meters by 2.5 meters, something like that, but a vending machine. The solar panels, which you can see in the video here, are rollout solar panels. That's one of the new technologies that's being tested out on DART. When those are fully deployed, then those are 18 meters from tip to tip, which is